This tells you flashing, freezing is extremely important for the food industry. This tells you in our home used refrigerator, you can only temporarily freezing a products. Usually will be 1 to 3 months. And you can do a comparison. A chunk of beef, you frozen half a year, a chunk of beef frozen 10 days in 1 month. You're not going to see the difference between 10 days and 1 month, but after half a year it looks horrible. And the lamb and chicken is even obvious because the muscle tissue is different. It's very interesting, these two curves. Okay, now, then the last two actually, we want to mention something else. So what's the food industry they're going to do? Since we have the rule here, large nucleation will generate large number of the nuclei will generate small crystal. We like it. And we don't want a small number of the nuclei generate a large size of the crystal. So what they do? And also we talk about the flash and freezing. There are a couple of works they can do. Number one, using nitrogen gas. If the food product is seasoning, okay, basically chicken fillet is not really, but they sometimes listed in the textbook. Salmon fillet, or some other seafood products, they were using not really nitrogen gas, I would say liquid nitrogen. They were using, quotation mark, okay? They will use minus 196 degrees Celsius liquid nitrogen. So think about that. If a food product you have a liquid nitrogen put in, what happened? It's like boring. Quotation mark. You have the fume going to generate, directly become a vapor. All those solids going to come. Looks like there's no ice. It's all protected by the vapor. So that's one of the methods what they do. The second method is do seeding. What's the seeding they do? There are 3 examples we can do. Number one, if they make a milk products, in the milk evaporator, they will add very small ground lactose. They can milk some of the milk products. They do that. Margarine. Okay, shortening and margarine, those 2 products we'll mention all the time during this semester. Margarine, what they do? In a heat exchanger, they add very small size of fat lettuce. They add them to let them. You manually added a lot of the nucleation, so let the crystal become very, very small. Okay, in the food microbiology area, what we do? How we storage a bacteria? This is some question I always ask. Okay, I have a bacterial solution. Let's say an E. coli. At 35 degrees Celsius, growing 24 hours at tropic soil blast. Do you think this is going to be stay there forever? No. Remember the bacterial growth curve? Is that right? We have lag phase, log phase, stationary phase, dash phase. This can stay there maybe 48 hours, 48 to 72 hours. So some students will say, how about let's put this in 4 degrees Celsius into refrigerator? How long it's going to stay? Around a week. Okay, if I want to permanently to storage this E. coli, what we do? We know that add glycerol. Is that right? We add glycerol. Actually, it should be a glycerol with semi-solid medium. And at the same time, you also need to add a little bit of sodium triphosphate. This is to neutralize the pH. What the name, the terminology for this glycerol? Cryoprotectants. That's a name for that. The sum of the products to use to protect the bacteria. So that's a very good example. There are lots of the cryoprotectants. Glycerol is one of that. Okay? Last thing, we also want to mention, I need to put some space somewhere on the top. Okay, number 5. This is a very common knowledge, but people don't really recognize it in the food processing. Water become ice. A very simple common sense. What will change? The density. Water is 1.0 ml per gram. What is ice? 0.9 ml per gram. So what happened when you frozen it? The food volume will be increased about how many percentage? Roughly 11%. That is not good. Why? Especially some of the products is related between fatty acids and the protein and the sugar. We call it emulsifying. If the volume is increased, the emulsifier could be breakdown. And for meat products, if you increase the volume, which means the bound water and lots of the free available water could be released, you're going to have an extra drip. That's not good, because we are talking about flavor, juiciness, and tenderness. Certainly the juiciness will be significantly decreased. The volume going to increase, so have to decrease the volume. What we do? There are lots of methods they can do. Our textbook uses a very old method. They mentioned a very old method back in 1950. They add sucrose. Sucrose is a non-reducing sugar. We'll mention it all. Very interesting. If you add 10%, the volume will be decreased to 8.6. If you add 30%, the volume will be decreased about 3%. If you add 50 to 60% of the sucrose, what happened? This is almost to 0%. So the older methods, what they do is add sucrose, and then the volume could be controlled very well. So that's something very interesting. Okay, there is a last question. Okay, question number 6. I didn't arrange very well. Just too many interesting things to talk. Too excited talk, so it's not arranged the blackboard very well. Last question we want to ask you. Last week is very cold, freezing, blizzard, you can say that. What you see they do? Did you see lots of the salts on the road. So we want to let the ice, snow melted quickly, so we spray the salt. It's a very simple question. Add sodium chloride, will lower down melting temperature of ice. What's the theory behind it? There is a true theory about it. Number one, sodium chloride could break down the covalent bonds of the water. How they break down? This is oxygen, this is hydrogen, and hydrogen. If you have a salt there, the sodium positively charged will be attached to the O. Okay, in other words, this Cl negatively charged will be connected to what? To the hydrogen ions, so they break it. Second theory is purity theory. Purity theory. This is not heard about much. What happened? This is water. When they become ice, or ice become water, they need purity. Which means they do not need any other ingredients there. Now, by the way, if they have other ingredients there, that will has another nucleation, which is called heterogeneous nucleation. That's more complicated. You can read at the Feynman book. It's completely physics and math and chemistry. We don't talk about that. So when the water becomes ice, ice becomes what? They need purity. Which means no other ingredients. If you have a salt there, what do? They will leave the ground to repel. At the same time, they will have a very tiny nuclear generator. And more salt you repel, they will generate lots of the nuclear. At the same time, they will have an intersection. This intersection has limited amount of the water. Those water are extreme, super cold. So let's say this ice is 0 degrees Celsius. This is maybe minus 10 degrees Celsius. And they will have a heat exchange. At the end of the day, we'll reach heat equilibrium. So the melting point usually is around minus 5 to minus 6 degrees Celsius. That's easy for them to melt. So there's a true theory about that. One theory, lots of the textbook studies break down the covalent bonds or hydrogen bonds between water, between oxygen and the protons. Second is a purity theory, because they want a purity. So if you add a salt there, they're going to be repel. At the same time, nuclei are going to be formed. But there's an intersection between that. The intersection have a very limited amount of the supercoiled water. And they have a heat exchange with the ice, or with the nuclei. They will reach a balance. The balance usually is about minus 5 to 6 degrees Celsius. It really depends on what type of the salt you use. The same as we did for the boiling temperature. You add different salt. Usually the melting temperature is a slightly different, but most of them around minus 5 degrees Celsius. That's what they use in the road in a blizzard day to do it. Okay? So that's what we have so far. Okay, it's already 1:30, so we'll just finish today, and we'll talk about